So, we have discussed so far that the main interest in aerodynamics is to determine the forces that are acting on a body which is moving through it, and we have mentioned that to do this what we need to know is the detailed flow about the body, the complete velocity distribution, pressure distribution, and once we know them we can find all the forces and moments that eventually will act on the moving body. Now, to do that, the first thing that we need to set up the equation of motion of the fluid or the flow, and this necessitates that we should have some knowledge about the basic properties or defining properties of fluid. Now, it is well known to you that the defining properties of the fluid is the ease by which a fluid can be deformed. If you compare to a solid, the fluids are deformed by a relative motion with respect to another, even subjected to a small force. For a solid, if we apply a small force, any deformation that may occur is negligibly small, while in case of a fluid it is not necessarily small. Of course, there are certain fluids which shows a dual behavior, that is, it behaves to some extent like solid and to some extent like fluid, and of course, we will not include that type of fluid in our discussion. As an example, say jelly, paint, peach, they have both this dual behavior. Sometimes they behave like a solid, in some respect they behave like fluid. Like peach as such is behave like a solid, but if a large force is applied on it for a long time, then it shows a fluid like deformation. Same thing about paint also. It usually does not show liquid behavior, but if you shake it or brush it, it flows with the brush. So, obviously, we will not discuss or not consider this type of fluid for our discussion, because mostly see we are interested in air, and of course, it is not necessary to discuss only air, because there are many fluids including both gas and liquid which have almost similar behavior. So, we will call these to be simple fluids, and we can define them in such a way that if we apply a force on this fluid, then the tendency of this applied force to deform it is not possible without a change in volume. That means, fluids are those substances which cannot withstand the tendency by an applied forces to deform it in such a way that leaves the volume unchanged. This you can of course note as a definition of simple fluid, that fluids are those substances which cannot withstand the tendency by applied forces to deform it in such a way that will leave its volume unchanged. And we will see what this definition actually means when we come to the forces that are acting in a fluid. Right now, we will say that this does not mean that the fluid cannot resist any deformation. The fluid can resist deformation, but it cannot prevent the deformation, and once the deformation occurs, along with the resistance also vanishes. So, this we will consider the definition of simple fluid, and you see the two most common fluid in nature, air and water, are quite easily explainable by these definition. And of course, we will not even use the term simple fluid all the time, we will just go on saying fluid, but meaning that we are excluding those special type of fluids, sometimes called thixotropic fluids, which has dual behavior. Now, as far as two different phases of fluid, the fluids are either liquid or gas. Now, as far as these two different phases of fluid, okay, the distinction lies mostly or in the what is known as the bulk modulus of elasticity. The liquids usually deform much less compared to gases. That is, due to a small force, the specific volume or density of the gas changes much more than the liquid. So, in any situation where the pressure change is large, then you see that this gas and liquids, they will behave differently. However, if the pressure changes are not large, then in the behavior of gas and liquid are almost same. In that situation, we do not need to consider any special property of gas when the pressure changes are not very large. Then there is no difference as far as dynamics is concerned of liquid and gas. Can you say some situation where the pressure changes are large from your say daily experience? No. One very simple example is the atmospheric flow. Particularly, if you are dealing with weather or meteorology, you need to consider the airflow in almost the entire atmosphere. And in this case, over the atmosphere, over the great height of atmosphere, the change in pressure is quite considerable. Another situation occur, that is in very high speed motion, not just say 50 meter per second or 100 meter per second, but much larger than that. In that type of situation also, the change in pressure is appreciable, and in that type of situation the special property of gas, that is large deformation, need to be considered separately. But in most other situation, the behavior of fluid in general, that is both liquid and gas, are almost similar as far as the dynamics of the fluid is concerned. And most of the time during this course, we will confine ourselves to that type of situation, where the pressure changes are not much larger, and any discussion that we make are applicable to all fluids, both gas and liquid. Now, we know that all substances are made up of certain molecules, and we also know that there is enough space between the two molecules. The molecules are not very closely packed, that it is not that all molecules are in contact. There are enough space between any two molecules. And what happened to the force between these two molecules? Just think about two molecules in isolation. Any idea how the force behave with distance? Inversely proportional to the that is for very large distance. Let us say the distance is
it drops for some time, and then after a certain critical
not for some time, not for some distance.
Certain distance, and then after some critical point it increases again.
Okay. Now, let us say if the distance is, see we are talking about now a distance which is fraction of nanometer, like say 10 to the power minus 10 meter or even perhaps smaller, which is small in the molecular scale itself. We will define two scales, which are molecular scale and another is macroscopic scale. A microscopic scale, which is the molecular scale, when we are talking about sizes, distance or everything as of molecules, and the other macroscopic distance which we commonly observe. If the distance is say a fraction of nanometer of the order of 10 to the power minus 10 meter or little smaller, usually the force between two molecules is a very strong repulsive force usually. This can also be very strong attractive force if there is a possibility of electronic exchange between the molecules. Let us exclude that case. So, in other case we have a very strong repulsive force between the molecules. As the distance increases in that respect in the 10 to the power minus 10 scales, as it increases at a certain critical distance, the intermolecular force between these two molecules drops to 0. Then again with further increase, the force now become attractive instead of repulsive, and in that distance, say when the distance between the two molecules remain say within about 10 to the power minus 9 or 10 to the power minus 8 meter, that is a nanometer to few nanometer, this force decreases or this force varies with distance to the power of minus 7 or minus 8. And then when it comes to macroscopic scale, what you are saying that the forces behaves inverse square. So, this is what is the variation. Now, what is the usual molecular distance in say fluids? The usual molecular distance is say 10 times or of the order of 10 times, it is not exactly 10 times. So, this distance is not a fixed distance, it varies from molecule to molecule. The distance is of the order of 10 times the critical distance in case of a gas. The distance between two molecules on an average is 10 times the critical distance between the molecule. The critical distance is the distance at which the intermolecular force drops to 0, which is of the order of say 3 to 4 nanometer usually, 3 to 4 nanometer. So, the average distance of molecules between gases is about 30 to 40 nanometer. In case of liquid and solid, it is of the order of that critical distance. In case of liquid and solid, the distance is of the order of critical distance. Now, when you see the fluid as a bulk, then now think that we want to have a plot of density versus distance. If we have a plot of density versus distance, how will the variation look? We know
increases, the density will decrease. As the distance increases, the density will decrease.
The density will decrease. Why?
Because the molecules are far apart, then the mass per unit volume will decrease.
It is not exactly so. See this, when the distances are very small, you know the density is concentrated in the nucleus of the mass is concentrated in the nucleus of the molecules. So, when you are thinking of distances which are say much less than this 30-40 nanometer, which we say the average spacing, within that distance in some position you might find some molecules, in some position you may not, and the density is violently non-uniform. It is violently non-uniform. Now, if we are considering a volume which has a diameter or characteristic size greater than this, then you see at any instant this volume will contain a large number of molecules. It will contain a large number of molecules, and consequently the density will reach to more or less a uniform value. So, for a very small, if we consider, say, instead of now just a distance, what we call a sensible volume, if we consider a very small sensible volume, then for extremely small volume the density variation is violently non-uniform. However, when the volume reaches to certain large value, again this is quite small, even in the macroscopic sense it is quite small. So, maybe even 10 to the power minus 15 or 10 to the power minus 12 cubic centimeter, even that type of volume will contain a large number of molecule, and the density will have more or less a uniform behavior. Now, think if we are using certain instruments to measure any property. I took density as an example, but this holds for any other property. Density, mass or specific volume, they are all almost related, but if we think about the velocity or any other property of fluid or flow, all of them behaves in the same manner, that when the sensible volume is extremely small in the microscopic sense or in the molecular scale, then the variation is violently non-uniform, but when it is small in the macroscopic sense, but extremely large in the microscopic or molecular sense, then we reach to a more or less uniform value. So, when we consider the bulk of fluid for our dynamical study, we see then that this particle structure of the fluid is practically of no importance, because see what we will be interested when we call, say, the density at a point or velocity at a point, we will be thinking of a sensible volume which is small in the macroscopic sense, but still extremely large in the molecular sense. In the molecular scale it is extremely large. When we will say a point, actually by that point we will mean simply a sensible volume of the size of, say, 10 to the power minus 12 or 10 to the power minus 15 centimeter cube, not smaller than that. So, as far as the dynamics of bulk fluid is concerned, that particle nature of the fluid is not important or will not come into picture usually, except in very, very special cases. So, most of the time we will not even think of this molecular structure of the fluid, we will just consider the fluid is a continuous medium, where density, mass or any of these properties are distributed continuously, and point in our discussion we will have that meaning, that the point is not a point in the molecular scale, but in a macroscopic scale. This hypothesis you know that already used for solids also. In case of solid also there is this situation is there, though of course, the sensible volume is much smaller, because the molecules are more closely packed, but there also it is actually in the molecular sense it is not continuous, the mass distribution is not continuous, there are also some space between two molecules. But in solid mechanics also we consider the same hypothesis, that the matter is a continuous distribution of mass. So, this hypothesis which seems to be quite natural. In the macroscopic sense, we can't think of, even our daily experience shows that the things are everything is continuous, the mass is continuous, the velocity is continuous. So, this is known as continuum hypothesis, and any mechanics that uses this hypothesis is altogether called continuum mechanics. So, all solid mechanics and fluid mechanics can be collectively called continuum mechanics. And then any difference that comes in solid mechanics or fluid mechanics is mainly due to the relative ease of deformation of fluid, because a portion of fluid can be much easily deformed than a portion of solid, or the relative motion over a portion of solid is negligibly small when compared to the relative motion of different portion of fluid. So, now we will consider the forces that acts in a fluid. Now, forces in general are of two types. The forces we will define them to be are in generally of two types. There are certain forces called long range forces, which acts when the interacting elements are a large distance apart. Think about a fluid or even a solid. There are two portion of the say two element of solid or two portion of this fluid which are interacting. One is exerting certain force on the other. Now, there are some forces which can exert even when the distance between these interacting elements is large. Of course, as the distance increases, the force decreases, but they still act. Even at a very large separating distance, the force is still present. You are very familiar with the most common example of long range force, which is the force due to gravity. Also, this force has a tendency that it acts over the entire volume. All molecules or all elements will, instead of molecules, we will call elements, which is not exactly the same. Molecule is a molecule, element is a fluid element is a very small fluid element, which may contain a infinite or infinitely large number of fluid molecules. Okay. So, it acts over all the elements or over the entire matter. This force acts over the entire matter. Consequently, these forces are also called as volume force or body force. So, they are called long range forces or volume forces or body forces, and the most common example is the force due to gravity. Any other volume forces or long ranging forces you are familiar with? Yes, electrostatic force. Magnetic force. Okay, let's call it electromagnetic force. Any other? There are certain fictitious forces, isn't it? Certain fictitious forces, particularly if you express the motion in terms of a set of accelerating axis. Yes, if we express the motion with reference to a set of accelerating axis, pseudo forces or fictitious forces, as an example the centrifugal forces, they are also body force or volume force. The other kind of forces are short range forces or surface forces. They act only when there is a direct mechanical contact between the interacting elements. And of course, the nature is the transport of momentum by the molecules, and that is why the distance is to be of the order of that molecular distance. That is, when the distance between the interacting element is of the order of molecular distance, which we can say is in direct mechanical contact, only then this force acts. This also you are familiar with. Rather, you call the normal reacting force. That is the nature of that, and the friction comes as a result of it. When two rigid bodies are in contact, see this force exists, even the friction comes only when there is relative motion, otherwise not. But the normal reaction, that is there whenever two rigid bodies or two solid bodies are in contact. So, that normal force is the actual force, which comes because of, in case of a solid, see the molecules which are vibrating, they penetrate one molecule from one body to other body. So, that is why that distance need to be so small. If the distance is larger than that, what we call the say of the order of the critical distance in terms of molecular scale, if the distance is larger than that, then this force will not exist. This force acts only when there is a direct mechanical contact. Now, as far as expressing the volume forces or body forces, should we write? So, volume force or body forces or long range forces, say two types of forces. Please make note even when I am not writing. It is not that what I am writing only that you will write. Mathematically, we will write this force in this fashion. Say in vector notation, we will write it, this rho is density, we will just bring in, because you see the most common volume force, gravitational force, it depends on the mass. Then the force per unit mass, F, in vector sense, acting on an element which has a position vector denoted by x. The x is the position vector, that means x has 3 component. We are not using x as x at time t. So, this is the, and of course, this multiplied by volume of the element. So, this is the body force acting on a small element of volume delta v, where F is the body force per unit mass acting at position x at time t, and this is density, rho is density. The common example is the body force due to gravity, and in that case this F is simply the gravitational acceleration g. Okay. For gravitational force, F is g. where g is the gravitational acceleration. The other force is the short range force or surface force. And in this case, of course, we cannot express this force in terms of say the volume, because this force acts only on the surface. So, the total force that acts over the entire surface of the element, of course, cannot be expressed in terms of the volume of the element. This depends on the total surface area of the enclosing surface. That is, think about that. Let us consider as an example that this is what is an enclosing volume. Then the surface forces acting on this element is simply depends on the surface area of this volume, of surface area of this enclosure. Now, you know that each surface area or each element of surface area has its own normal. So, even writing surface force per unit area and then multiplying by the whole surface area is also meaningless, because the surface area has its own orientation. So, this orientation must also be taken into account. Then this surface force then depend on the elemental area and its normal. So, let us write that surface force acting on an element of area say delta A with normal n or unit normal n. Okay, for the time being I am using this vector notation. Let us denote it simply by should we denote this x also in vectorial sense? In that case, earlier also we should denote it as the vectorial sense, that this is the position vector. So, that means this element we are considering which has a position x at time t. This is how we are just denoting it, but this is what we have denoted it. Now, let us say that let us say that in this case this is what is the force acting on this element and the normal is also in this direction. That is, this part of the fluid to which this normal direction points, this part of the fluid, let us say this is only fluid, outside also fluid and inside also fluid, and this is an enclosing area. Then the fluid which is outside, that is exerting a surface force on the fluid which is inside, and let us say that is what this T n x t, what we have written here. Then what will be the force that is this inside fluid is exerting on the outside fluid? Yes. Yes, negative of this. Okay, fine. So, on the other part, T, by the definition of this symbol, can't we write that it is also this? If we change the direction of the normal in the other way, that gives the same force. And what does it mean mathematically? That the surface force is an odd function of the normal. The surface force is an odd function of normal. Now, before we proceed further, we will talk about a little bit about the notation that we are going to follow for next few days, the general notations that we will be following. Of course, we may come back to our usual convention of the axis system being x, y, z later on, but for the time being we will denote the three mutual orthogonal direction by x 1, x 2, x 3, say notation. Three mutual direction of three mutually orthogonal direction x 1, x 2, x 3. We will see that this is we are doing for some convenience, so that we can write whatever we want to write in a much more concise form, instead of if we write them in x, y, z. Similarly, any vector which has say 3 component, again we will denote them by the subscript 1, 2, 3. Like the force which has a 3 component, we will denote them by F 1, F 2, F 3 as an example, that body force per unit volume, or this T, these forces F on T, they will also be denoted, the 3 components of them, by F 1, F 2, F 3, T 1, T 2, T 3, and this further we will write usually as x I. For I equal to 1, 2, 3, they becomes x 1, x 2, x 3. In this notation, this is called this index notation. In this index notation, all vectors are denoted by with a subscript I. A letter with a subscript I represents a vector. So, if we call velocity vector, we can simply write, say if u denotes the velocity, then u I, it means it is a vector, it has 3 components u I. So, whenever if we see f I means it is a vector with say 3 components, if we are considering of 3 dimensional space, then it has a component of 3, f 1, f 2, f 3, and f I simply means vector, or any letter with a subscript I or any other subscript represents a vector. So, vector is represented by a subscript I subscript. In your vector mechanics, you used an arrow over the letter, here we will be using a subscript I. And the most usefulness of this notation is that any index repeated in a term represents a summation. If an index is repeated in a term, it represents summation. Repeated index in a term no sigma sign is required. So, as an example, see this is a term, this is one term where this I is repeated. It means, so whenever this term is there, it means similarly, you see if we write we do not need to write that sigma j equal to 1 to 3, that is not required. This automatically means this. Now, look to the second expression that I have written a j b j equal to a 1 b 1 plus a 2 b 2 plus a 3 b 3. What does it imply? See, a j is what? Is a vector A, b j is another vector v b. So, what is this a 1 b 1 plus a 2 b 2? So, this is what is vector dot product. So, dot product is written simply like this. We will define two special term or special notations, but before that we should talk about that vector needs one index, vector has 3 component. So, one subscript needs, but there are certain quantities which has more than 3 components. You have already come across stress, strain, which are force per unit area, and since both has force has its own direction, the area also has its orientation. Consequently, the resulting term has this 2 in them, that is they have a component in a particular direction. Also you need to specify the area on which they are acting, and that area is specified by its normal. So, you need to specify 2 particular direction to express stress. So, this type of quantities are called tensors, and tensors are represented by 2 subscripts. The tensors are represented by 2 subscripts. Or anything you go on writing. Any tensor you want. Whenever there are 2 subscripts attached to a letter, it represents a tensor. And the stress and strains are the familiar example that you have already come across. We will define 2 special tensors. One is a second order tensor known as delta I j, known as Kronecker delta. So, as you can see that I j, if we are considering 3 dimension, then I can take the value 1, 2, 3 and j also can take the value of 1, 2, 3. So, this sigma I j has 9 elements, or sorry, delta I j has 9 elements, delta 1 1, delta 2 2, delta 3 3 and so on. Now, this delta I j has a special meaning that it has a value equal to 1 if I equal to j. When I and j are same, if we represent this delta I j mathematically, this also can be represented by a matrix having 9 elements, a 3 by 3 matrix. So, I equal to j means the diagonal elements. So, the diagonal elements are 1 and all other off diagonal elements are 0. So, in the matrix representation, this is simply the identity matrix. The other one is epsilon I j k, called the alternating tensor. As you can see, it is third order tensor. It needs 3 subscript to express it. Third order tensor, meaning in 3 dimension it has 3 by 3 by 3, that is 27 elements, total 27 elements. And here also the elements have pre assigned values. It is like that, epsilon I j k equal to 0 if I j k are all not that is all of them has to be different, then it is 0. Even if 2 of them are same, it is 0. When 3 of them are same, of course, it is 0. When 2 of them are same, any 2 of them are same, it is 0. So, for non-zero value, all 3 must be separate, different, and it is 1 if I, j, k are cyclic. When they are different and cyclic, different is already, because the first condition gives, if not different they are 0. So, now if when they are different, if they are arranged in a cyclic order, it is 1, if it is not, it is -1. So, you can write if otherwise, if not cyclic. And you can see the where it is required. In this index notation, this alternating tensor comes to represent, say, the what we call the cross product of two vectors or the vector products. So, to represent vector products, we need alternating tensor. So, that is two vector denoted by A cross B is in index notation can be written as epsilon I j k A j B k. Epsilon I j k A j B k, and you can, if you try to expand this I j k, you can see that for each I you will be getting the 3 component of this left hand side vector. I want to take an example. Let us say the I for I equal to 1, what do you get? For I equal to 1, first of all you think what are the non-zero component? Looking to epsilon I j k, if I equal to 1, then j and k cannot be 1, because that means 0. For any value of j and k 1, it is 0. So, there are two possibilities, that j equal to 2 or 3 and k equal to similarly 2 or 3. Now, and of course, they have to be different, j and k are not same, because if j and k again become same, then epsilon I j k will again become 0. So, when j is 2, k is 3, and when j is 3, k is 2. So, these are the two possible non-zero case, j equal to 2, k equal to 3, which makes A 2 B 3, and in that case what is this epsilon 1 2 3, which is cyclic. Okay. So, 1 2 3 that is positive. So, the non-zero component is A 2 B 3 minus A 3 B 2. Is not it the ith component of A cross B? Similarly, you can check it that this is. So, what a vector product is denoted by this notation epsilon I j k A j B k. One thing you must remember, that in a those indices which are repeated, they are also called dummy indices, and dummy indices can be changed at any time. So, it is not wrong that if one step you write d u I d x I, and in the next step you write d u j d x j, it is all right, because both means the same. Of course, these are the basic introduction of these notations, index notations, and anything extra if required we will explain whenever it comes. But with this now we will go back to that surface force that we were discussing earlier, but I think we will wait for a few minutes for that.